Good day, listeners, and thanks for joining us. My name is Oliver White, Chief Storyteller at Lightbend, welcoming you to today's webinar, Using the Actor Model with Domain-Driven Design in Reactive Systems, featuring our special guest and industry luminary, if you don't mind me saying so, Mr. Vaughn Vernon. While I introduce today's speaker and topic, I would like to ask our audience a pretty straightforward poll question. What is the worst pain with your current system? For those of you who don't know Vaughn, he's an author, speaker, trainer, and consultant who has been helping people build systems better for nearly 30 years, focusing on domain-driven design and reactive software development and emphasizing simplicity whenever possible. Vaughn has written 3 books implementing domain-driven design, reactive messaging patterns with the actor model, and domain-driven design distilled, all published by Addison Wesley. With such a distinguished past, I wanted to invite Vaughn to join us today to discuss the actor model, domain-driven design, and reactive system design, and how it all comes together. As Vaughn will show you, the actor model isn't just some new fad among a small group of developers. In fact, the actor model was first designed in 1973, over 20 years before brands like Yahoo and Hotmail first showed up on the young internet. It was created to address the long-term direction of computing and software development, and it's almost as old as the OOP model itself. And according to Forrester Research, the actor model is seeing renewed interest as cloud concurrency challenges grow. This is why enterprises like Intel, Samsung, Walmart, PayPal, and Norwegian Cruise Lines are embracing the actor model with Akka and building distributed reactive systems to manage today's demands, especially preparing for the upcoming IoT wave, which, as you may guess, promises to add billions of connected devices to our lives. So today, Vaughn explains why actors are so vital to the future of software development. You will learn why actors are so exceptionally well suited for use with domain-driven design, how they're designed to gracefully handle failure and maintain resilience and responsiveness to users no matter what's happening, and how actors help you reactively scale your systems to meet concurrency demands, elastically growing in and out to handle peak load and shrinking when not needed to minimize your infrastructure and hardware footprint. I will close the poll. Today's webinar is supported by our hundreds of happy subscribers, particularly Starbucks, a company that you may have heard of before. Starbucks is looking for several software engineers to join their team in Seattle. So if you're interested, have experience with Akka, Scala, Spark, and Cassandra, and enjoy what I can imagine is unlimited coffee. You can find out more about this position and other open positions with our customers on our website under the Company tab. As always, this webinar is being recorded and will be emailed to you in the coming days. If you have any questions, add them to the GoToWebinar control panel, and we'll see if we can get around to them into the Q&A part of today's session. If your organization is a Lightbend subscriber, you can log into our customer portal and send all of your technical questions to our support engineers there. All right, that's all from me. I'm very happy to hand it over to our special guest, Vaughn Vernon. Hi, Vaughn. Thanks so much for joining us today.
Thank you, Oliver, and thanks to everyone at Lightbend for inviting me to, pardon me, to speak and share some ideas about the actor model and domain-driven design within reactive systems. So if anybody would like to contact me, here are a few ways to do that. I'd be happy to answer additional questions in email after this presentation. As Oliver mentioned, these are my books, and so this presentation is actually a sort of fusion based on my domain-driven design ideas as well as the actor model. The Reactive Messaging Patterns book is specifically a Scala and Akka book. So just to kind of give an introduction to where this presentation is headed, I just wanted to kind of state the obvious. When we're using objects and the typical object-oriented programming language, every single method invocation from, for example, a client upon a server is a blocking invocation. And when I use the term client and server here, I'm not talking about heavyweight components. I'm really just talking about simple objects. So we have an object that is a server and an object that is a client, and when it makes a method invocation, it blocks. If you look at the trends in processors, microprocessors from the year 1973 to the year 2003, you'll notice that things have changed a lot more recently. Going back to 1973, processor clock speeds were running at less than 1 megahertz, and maybe there were about 4,000 to 5,000 transistors in a microprocessor. Moving up toward our recent times, you can see that processor speeds and numbers of transistors followed the Moore's law prediction that we would see increases every few years, and this climb continued. But notice in the year 2003 what happened to clock speeds on processors. This is probably no news to most of us, but clock speeds really tapered off to the point where speed increases became relatively flat. Now, this isn't to say that processors today aren't achieving additional benefits, but in general, it's difficult to, for various reasons, to get increasing clock speeds out of processors today. And of interest is the fact that I used the year 1973 as a starting point, and I'll get back to that in a moment. So today, what really matters in servers, for example, are the cores, the numbers of cores that processors support. There are many more cores, but yet not much faster cores than there were even 12, 14 years ago. So the cores really matter in this equation of how we're going to deal with the future of computing. So with all these cores, our thoughts might go to, hey, threading is easy. I know what I'll do. I'll just create a work queue, and we'll have one thread dedicated to enqueuing new work tasks, and then we'll have many threads, perhaps, reading from that work queue, and they'll be off on their way to concurrent work tasks and accomplishing a lot of throughput using all these new threads. And when we think about that, the threading model in that way, it seems really easy. It seems like there's very low risk in approaching this. But in reality, threading is hard. Think about this work queue that I've described and what will actually most likely happen with it. We see that there's actually one thread, thread 4, that is accomplishing something. Threads 2 and 3 have to block because they're waiting for thread 4 to finish its access of the work queue. They will eventually get access to the work queue, but they're blocked right now. That's because there's a lock on the work queue when there's someone reading it. And also thread 1 needs to write to the work queue, and because there's the possibility of some collision on the work queue, thread 1 is also blocked, so it's not enqueuing new tasks. Okay, maybe that part of it, thread 1, isn't so bad because it will eventually and most likely stay ahead of threads 2, 3, and 4, possibly. But notice what happens when threads 2 and 3 read new tasks finally off of the work queue. Thread 2 perhaps gets a new task and starts to operate on an entity. thread 3 then gets access to the work queue, but then blocks because actually the task that thread 2 and 3 just read are both directed onto a single entity instance or object. So now there's blocking on the entity. They've already experienced blocking on the work queue. And essentially, if we're not careful, what happens? Well, we turn our multi-core processor and our multi-threading application into essentially a single-threaded application, or at least one with a high level of contention among working threads. So threading is hard. On the other hand, the actor model is designed to be message-driven, to be non-blocking, and throughput is part of the natural equation of the actor model. Here, a sender sends a message to a receiver. Now, if you think about the actor itself, it's not much different than a simple object, and that's key. We don't want you to go away from this webinar thinking that the sender and the receiver here are some sort of heavyweight component. Essentially, they are the same as normal objects, but they have a few additional mechanisms that allow them to be message-driven and to deal with messages that are being sent and delivered in an asynchronous way. So when the sender sends this message to a receiver, what happens? As soon as the message is enqueued for the receiver, the sender continues on its thread of execution, and the receiver will process the sent message on, let's say, a different thread at some time in the future. So when you get a lot of actors processing, you basically have execution context switches going on all the time as senders and receivers are both sending and reacting to messages. And one more point that I want to make here is that sort of, one of the obvious luminaries in the industry and the sort of, person who defined a lot of the object idea in the first place emphasizes that the big idea is messaging. So Alan Kay, the inventor of the small talk language, really had a focus originally on messaging between objects. And he's even gone so far to say that the internal implementation of the objects was not his focus. And it seems like that's where developers actually put a lot of their focus today, is on ideas such as single responsibility principle and maybe Liskov substitution principle, some of the solid ideas. But when you think about it, what really states the purpose of two objects is the kind of object that they are and the messages that they exchange. And in fact, the small talk language was based on message sending. Even though it wasn't originally an asynchronous model, it still was a model of message sending. So one object would, in essence, send a message to another object to get anything done within the small talk model. So the actor model is actually adhering to primarily the ideas that Alan Kay originally had about objects in the first place. So the reason that I noted the year 1973 in that previous chart is because that's when Carl Hewitt, the inventor of the actor model concept and the actor model of computation, started his development in 1973. Now, if you look at the history of objects, Simula was starting to be created somewhere around the year, I think it was 1967 or 68, and this had an important influence on Alan Kay as he was developing Smalltalk and really tuning the ideas behind objects and providing an environment for objects to be developed. And there was a Smalltalk 71, as in 1971, and then Smalltalk 72, which somehow, I don't know the exact history on it, ended up in the hands of Carl Hewitt. And Carl Hewitt was inspired by the progress on the ideas behind Smalltalk, and this helped him to formulate his ideas around the actor model. Now notice, again, to draw attention to what processors looked like at that time that Carl Hewitt was starting his work on the actor model, clock speeds were below 1 megahertz, and the number of transistors in processors was about 45,000 or so. So Carl Hewitt's work was way ahead of its time, and his vision was for multi-processor systems and very fast networks. And so he was developing the actor model with what ended up being the condition of most servers or computers to be very far off from the time of 1973. Well, some years passed, and there was another use of the actor model in Erlang, and then Jonas Bonér saw the vision that actors on the JVM and a robust actor system, or the ability to build robust actor systems on the JVM, was very important. So again, Jonas is a real luminary in the industry foreseeing the need to do this. And this set off with creating Akka the opportunity for most of us to use actors on a very familiar platform, the JVM. So thanks much to Jonas for that. So let's just talk for a few minutes about actors and how they support reactive. Reactive is defined as having four main characteristics. Reactive is responsive, reactive is resilient, reactive is elastic, and reactive is message-driven. And message-driven is what basically allows these other three characteristics of reactive to be supported. So let's look at responsive first. Reactive is responsive in that we can respond to user demands and increasing demands on a system because of the reactive characteristics of a system. And it's not uncommon for a reactive-based system to be able to respond to user demands in a request-response fashion, let's say through a REST request or a normal web request, in sub-25 millisecond time frame. So in supporting reactive through the actor model, we're able to see very high throughput, and this has been well proven over the time of Akka being available. Another characteristic of reactive is that reactive systems are resilient, and resiliency is also supported through message passing or being message driven. And the idea behind this is that when a client actor, for example, sends a message to a server actor receiver, note that that client does not have to deal with any exception handling that may be caused within that server object or actor. Normally, when we're dealing with objects, and if our object-oriented language, such as Java or Scala, is dealing with a client sending or invoking a method on a receiver, it's the client that will have to deal with any sort of crash or exception being thrown. And it's become pretty typical for a client to actually just rethrow or toss the exception up to some higher level component and hope that someone deals with it. Because what is the client going to do about a server crash anyway? But in the actor model, especially with Akka, there is a hierarchy that's established for supervision. And in the case where a server crashes, and I'm talking about a server actor again, a lightweight, very lightweight component that is processing messages, if it crashes or throws an exception on one of those incoming messages, it's not the client that has to deal with that crash, it's the parent of the server actor or object that has to deal with that. So the parent is in a much better situation to understand the possibilities of crash on its child actor and therefore can react to it, restart that actor, and then actually the client only has to deal with the knowledge that it has either received a response to its request or it has not, and based on a timer or scheduled event can ask the same actor for the same request to be handled again if it doesn't receive an acceptable or a response within an acceptable time frame. So actor systems are very resilient, or have the potential for being very resilient when they're built correctly. Reactive systems are also elastic. They can grow and shrink according to current demand. And again, all of these are tied in by the fact that reactive systems are message driven. All of these qualities or characteristics of a reactive service are supported by this idea of being message driven. So why does the actor model make so much sense now? Well, as I already stated, cores matter, but we also have the opportunity in this point in time to take advantage of very high-speed storage devices, lots of memory, all kinds of devices that are available, whether they're IoT devices or mobile devices, and these are all highly scalable and widely connected, and we also have fairly affordable cloud hosting solutions and fast network. And all of these things are relatively inexpensive at this point in time. And again, I want to focus on the fact that cores are available. Think about this specific processor, the Intel Xeon processor. A single Xeon processor has the capability of supporting 88 cores. And if you actually join multiple Xeon processors as co-processors through the Xeon Phi technology, you can actually support more than 200 cores in a single server. Now, think about the opportunity that we have to use those cores, but the pressure that that puts on us as developers to be able to deal with multi-threading. Well, the actor model solves this problem for us in a very, very, very easy way or simple way for us to program against multiple cores without having to take on the cognitive overload of what is normally faced by a multi-threading environment. So we really think of the actor model as being a concurrent and parallel environment, and the focus is on concurrency, and the focus with the actor model is taken away from multi-threading because a toolkit or framework like Akka takes that burden off of the programmer. Also, another important factor with using the actor model is because every request and every response is asynchronous, it helps us to embrace the idea of latency. And as systems today become more and more distributed, latency is a matter of fact. Our distributed systems can be interrupted by some sort of downtime or partition on the network. It can be caused by various servers going out of commission, and because of this, latency occurs. The whole idea behind blocking requests through the object model becomes very unrealistic to use in a distributed system if you want your systems to be robust. So using the actor model, we actually build in a mindset and design in latency into our systems automatically. And because of this, we don't expect immediate results, and we only react to messages when they occur. And if there's latency between a request and a response, then that's already acceptable because we're expecting that, and that delay is designed in. Another important factor that I think the actor model helps us to solve is doing more with less. And what I mean by this is some of you are probably listening to this and saying, well, look, I'm not Amazon scale, and maybe I'm not Netflix scale, but that is not necessarily the focus that should be gleaned from this information. Actually, what if the solutions that you're using right now have 100 or more servers because the technology that you're using requires you to scale out to even that extent? Compared to Amazon, that's a relatively small cluster of machines or set of machines. On the other hand, what if you could scale those machines, the number of those servers, back to perhaps 5 or 10 servers and be highly over capacity or over I've just lost my wording on that, but essentially be to have much more scale than you actually need. So this is an important factor with the actor model, is getting the very most out of every single server, and there's a very high potential for being able to scale back your clusters to a great degree. So again, actor model is focused on direct asynchronous messaging. So a sender must know the receiver's address in order to send a message to the receiver. Actors are lock-free and they share nothing. So if these three senders send a message each simultaneously to a receiver, the receiver has those messages enqueued on its mailbox and will actually process them one at a time, so the receiver does not need to lock internally to protect its state from multiple threads operating on it at one time. And the receiver does not share its internal state with any other actor. You also have the opportunity with the actor model to prepare your receiving actor to handle its next message. For example, when the sender at sequence 1 here sends a message to receiver of 1, receiver of one reacts to that message and then becomes another kind of message listener, such that when the sender of message in sequence 2 is sent to the same actor, it actually responds using a different set of logic in its receive block. Actors come in systems, as Carl Hewitt says. One actor is no actors. Actors come in systems, and Akka supports a hierarchical actor-based system that allows for supervision and crash protection. And this is an illustration of actor concurrency and how in this diagram you can notice that some of the sequence numbers are repeated, such as 2 occurs twice in this diagram. This is not a mistake. That is because a router enqueues a scheduled timer at the same time, essentially, that it is sending a message to a receiver. And then at the same time, there's a potential race condition. Will the receiver of the router's message respond with a success before the timeout occurs? And so steps 3 are, in essence, a potential race condition. This doesn't mean that the router is susceptible to a race condition. It just means that the timeout or the succeeded message may occur or will occur one before the other. And so if the router receives the success event before it receives the timeout, then it will reply in step 4 to the client with a succeeded. However, if the timeout message occurs before, and the corresponding message is sent before the receiver replies with a succeeded, then a timeout event will be sent to the client. So how many actors can an actor-based service have? Do you think 50? Maybe 100? Well, if you guessed either of those, you would be right. In fact, if you guessed 1 million, you would still be right, because an actor-based system can support millions of actors potentially. Now, here's another contrast that I like to make. In a typical N-tier architecture, or what might be called a ports and adapters based architecture, there is what I think a lot of unnecessary complexity, maybe even accidental complexity. And if you take this ports and adapters architecture that's supporting an N-tier model, notice if we tip that on its side, that this becomes what I call a complexity stack. Look at the kinds of components that anyone working on this service will need to understand. And given the architecture and the architectural mechanisms involved, you may have more or less complexity here. But what I think that one of the biggest advantages of using the actor model is that you can collapse a lot of this complexity and just drop down to, for example, a set of adapters on the outside of the architecture that are, for example, controllers, and the controllers can delegate by sending messages to a domain model, and the domain model emits events. So I think that the use of actor model can be quite simplistic. So how can domain-driven design be an asset to us? Well, another true industry luminary is Eric Evans and the work that he put into domain-driven design. And in fact, if you look at the trends, domain-driven design is growing in popularity, and I don't mean popularity as in just a popular topic to talk about, but actually a technique for developing software that is becoming much more accessible to individuals, and they're making more use of it. So the community around true domain-driven design users or developers is growing. So what can we learn from what Eric Evans has said about domain-driven design? Well, the essence of domain-driven design is modeling a ubiquitous language in a bounded context. And quite frankly, we can boil much of the ideas behind domain-driven design down to this, or at least this is where I think the heavy focus is. This has become what I think is the real emphasis. So think about modeling a service of some kind as a bounded context, and the bounded context is a semantic boundary where everything inside that context, including the domain model, has specific definitions, specific meaning, and there's a language that's spoken by teammates that help us to understand what each of the concepts within the bounded context means. So that's going to be our focus. There's another important part of domain-driven design, which is context mapping, which really results or has the has the purpose, I guess I should say, in modeling how each of the bounded contexts that are in a system, how those correspond to each other, what are the team relationships, and what are how do the models interact, as in how do they integrate. So leveraging context mapping is also very important because bounded contexts tend to be much smaller than what many are used to in developing, and that would be with a monolithic mindset. So I think what I see today is that responding to rapid new business direction is a big challenge for just about any enterprise and the teams that work in the enterprise. And I think that DDD enables the necessary knowledge crunching in dealing with these rapid new business directions that teams have to respond to, and actors and messages potentially help us to rapidly implement the domain models and in response to those demands, and to have clear understanding about the domain models. So again, to quote Alan Kay, the actor model retained more of what I thought were the good features of the object idea, and also, again, the big idea is messaging. So if we take those two statements from Alan Kay and apply them to domain-driven design, what do we get? Well, in developing our ubiquitous language, we're going to focus on the actors as being the objects or the components, the elements of our domain model, and the messages sent between them as also part of the ubiquitous language. So for example, I have a product actor and a backlog item actor that are shown here, and a command message or a request is sent to a product, and the product emits a domain event, and a task or a defined task command is sent to a backlog item actor, and the backlog item actor emits a task-defined domain event. So this is all part of the ubiquitous language. The messages being sent, the actors that are responding to the messages, and the events that are being emitted. So how do we accomplish dealing with the rapid demands of new business ideas and direction? I think that event storming is an excellent way to do this, and there are many, well, at least a few correct ways to use event storming. One of those is through big picture modeling, but another way is, after doing big picture modeling, is to focus at the design level and perform design level event storming. And I think that this approach works very well for getting out of the minds of business experts as well as the development team how they will model new ideas and do so rapidly and respond to that. So I suggest looking into event storming. My DDD distilled book explains at least one approach to event storming, and Alberto Brandolini is working on completing a book on event storming, and since this is his invention, I recommend that you look into his book as well. But basically the idea is once we've stormed out our aggregates or our entities, which are implemented as actors, and we understand the commands that are being requested or can be requested of the aggregates and the events that they emit, this is what we end up with, is a client sender of a command to an aggregate or entity. The aggregate or entity emits an event. The event is asynchronously stored in an event journal, and the event journal can then be consumed in various ways. And actors as aggregates make an excellent consistency boundary. It is a transactional boundary that I think well meets the original purpose behind the use of aggregate. In the actual aggregate implementation using the actor model, what I like to do is implement an immutable state object or record within the actor. This can be done in Scala using a case class, for example, and actually you can have just one mutable state on the actor, and that is the var that is used to actually hold the state object or record, and as incoming commands are handled, then that state object, which is actually itself immutable, will be transitioned through a side effect free behavior or a function, and the results of that function is a new instance of the object or the record, and it is set on that immutable state. So there's actually just one place where mutability occurs on the actor. This is very important for testability and being able to reason about potentially a complex aggregate. Also, emitting the corresponding event is important, and all of this is supported by the Akka persistence part of Akka and a persistent actor trait that's available for creating your aggregates. And then what we end up with is, because events are emitted from one service, or if you like to think about a service as a bounded context, I think that this can map very well. An event is emitted to some sort of central high-performance bus, and it becomes a message to a topic, and that topic then is subscribed to by multiple bounded contexts or microservices, and as the events are being distributed to each of the consuming microservices, we're actually able to model full reactive systems. Again, as Jonas likes to say, reactive services, or one reactive service is no service. Reactive services come in systems, and so what we're ultimately trying to accomplish here is building full systems, not just single services. And by emitting domain events to other bounded contexts or microservices, we can accomplish modeling entire or developing entire systems. So there are more resources that Oliver wanted you to be aware of, and so you can look at reading Designing Reactive Systems with the Actor Model, which is a free O'Reilly book. And I think this is Jonas's book and Victor Klung's book, and I've read this book. I believe that's the same one. Maybe
Actually,
Oliver can.
this is written by a new author, Hugh McKee from Lightbend.
Oh, okay.
Although
Okay.
we do have books by Jonas and others on our website.
Okay, cool. Thanks for correcting me on that. And then also watch The Benefits of the Actor Model for Cloud Computing, a pragmatic overview for Java architects. And then Lightbend provides expertise around their platform, and you can engage with Embedded Lightbend Engineer, or ELE, for kickstarting your reactive initiatives. And then another important resource is the upcoming Reactive Summit, which will be held October 18th through 20th, 2017. And I really look forward to that. I hope that I'm able to attend this year. I wasn't able to last year due to being out of the country on an engagement, but
That's a
I
poor
really look
excuse,
forward to.
Vaughn. Out of the country. No.
But
Well,
well,
we hope to not only see you at Reactive Summit, but I would love to be able to have you speak there again if I have any power over that situation, which I don't.
well, thank you very much. And so I guess I'll turn it over to you, Oliver, and um, that's all I was gonna say. Again, here's my contact information, and maybe I'll just roll back to the Reactive Summit, or
Well,
which would you prefer?
we will be sharing all of this information in the next few days, so don't worry about that, folks. You'll be receiving an email from one of my friendly colleagues at Lightbend, giving you access to both a slideshow with the links inside and the video as well. You're also welcome to email me at oliver@lightbend.com if you have any questions about some of this, some of the last few slides here. So this ends our presentation. We do have a handful of questions that I think we have a little bit of time for. So we are happy to stay on the line for a few minutes for those of you that have time. So Vaughn, first of all, thank you so much for this excellent presentation. I thought that I knew a reasonable amount of this content, but it turns out I'm always learning stuff. So there's been a few questions around this, and I tried to consolidate it into a more simplified format. For our listeners that are working with a traditional Java EE or Spring app, what does it look like from a work perspective, or as well as an architecture perspective, between the actor model and, let's say, the traditional, I don't know, would we call it thread per request model or something like that?
Yeah. Well, let me back up here. Um, Let me see, where was that? Yeah. So where I think the difference is let's say that your web uh, server is implemented using Play Framework. Play Framework is a highly asynchronous web server, and so an incoming request that's being handled by a controller, for example, a controller class, is operating in an asynchronous way in the first place, but then when you actually send a command message like order book that you see here directly from the controller to the domain model, first noting my main point about this was that you're cutting out some of the normal architecture and therefore simplifying the application. But the command message that's being sent to the book object or actor is actually itself asynchronous. And so the thread that was being used for handling the web request can now be reused for handling another web request at the same time while the book is processing the order book command message and emitting the book ordered event to the event journal. This is all happening asynchronously. And then finally, the book sends some sort of response or result message back to essentially what is still a component that's you know just sort of inactive at the moment in the web tier. And when it receives that response message or that result, then it again gets a thread of execution and ends up producing a request or a response to the HTTP request. And this is all happening in a non-blocking way. And yet the browser hasn't had its request time out yet because it's all happening very rapidly. And so I think that the difference is there is no single thread of execution where the controller and then the book and then the event journal is running on that same thread and potentially blocking while, well, definitely blocking while the book ordered event is being saved or persisted into the event journal. So there's a very high throughput and multiple threads actually probably servicing this single request at different times. I hope that answers the question. It is logically the same and yet vastly different in the underlying actions that the system is performing in behalf of the components.
Well, I personally think that was wonderfully explained, and that may be the most clear explanation I've heard personally, and I'm not just blowing smoke in your direction, Vaughn. Another gentleman asked, kind of admittedly with a little sarcasm, so the actor model is kind of not, to use the actor model on a single core would be kind of defeating the purpose of concurrent computation, which it's so famed for. So the example you were just showing, if we were back 15 years ago and we had, single core machines and single threads, this process would actually take longer than, or it could potentially be a more, it could have higher latency than previous styles of doing things. But once we start spreading the work across 72 cores and rolling that out across 1,000 nodes, this becomes this incredibly rapid machine.
Well, how I would reply to that is I would say that you would have to ask Joe Armstrong, who invented the Erlang programming language and one of the sort of modern day implementations of the actor model through Erlang processes. And I think that Ericsson's use of Erlang and the actor model was very successful even on what we now consider archaic microprocessors. So actually I don't know off the top of my head a clear answer to that, but actually what comes to mind is a statement that I think I recall Jonas Bonér making, and that is that in a single straight line process, the actor model may take slightly longer in some cases than a single threaded solution if that single threaded solution is only blocking at each method invocation and not blocking on I/O. Okay, so let's set a context for that right there. So it may actually take the actor model longer to process on a single thread, a single request, because of the task switching or the context switching. However, when you consider the overall throughput of the entire application or service that's being accomplished by multiple threads, the net effect is far greater and much higher throughput than any comparative thread per request model could actually accomplish. So the
Good point.
the total is, or how's that, the something is greater than the sum of the parts.
Sum of its is greater than the sum of its parts, maybe.
Right, something like that. Yeah.
Uh, let's change directions a little bit. You showed a slide with the title "Event Storming" a little bit later in the presentation. Would you be able to define event storming a little bit deeper and how it's connected with microservices architectures, which is in the following slide, and event, or is it related to event sourcing and CQRS?
Yeah. So there are at least a few ways to use event storming, at least from my perspective. One way is called kind of big picture storming, and big picture storming is where you're trying to understand a very complex system, and you need to get the right people into the room so that the right people who have, the people who have the right questions are talking to the people who have the right answers, and you're storming out this, the concepts behind this, and it is at least initially based on using events. So your focus is first and foremost on events, which gives you a business process focus rather than a data focus. Now, it doesn't mean that you absolutely can only put sticky notes, the orange sticky notes up on the wall, and that you're absolutely prohibited from putting command messages or other kinds of stickies up. But primarily, you're initially focused on the events, the things that happen in the system. So along the way, you start identifying, okay, these are the commands that cause events, and then my focus here is on the actor that receives a command and emits an event. And so this is actually, this view is sort of boiling down to a more design level storming approach. So we're actually trying to understand the components that are being used to implement inside the model, inside a bounded context, but you don't have to use event storming this way. In this view that you're seeing, it is closely attached to event sourcing, and so which does meet up with Akka persistence and the persistent actor in a very sort of one-to-one way. It doesn't mean that you'll storm out every command and every event that happens. You probably need to think about the model at a different level, but at least you can get some good ideas to performing rapid modeling in this way. So I just say, look at Alberto's work and what he has to say about it. I think there may be a few other sources to event storming. I've made some comments on it in DDD Distilled. I think it's very useful. I see, the light bulb go on every time that I use it with clients or when teaching a workshop, and so I think it's very, very useful.
Great, thanks for that, Vaughn. We just have time for one more question, and there's been a few questions coming in about kind of relating this all back to some of the more timely apps and services available nowadays with the third wave of IoT, 50 billion devices and talking toasters and so on. How do these fundamentals play a role when it comes to, a new device that's doing real-time decision making and personalization, for your preferred level of toast and so on.
Yeah. Um, so I'm actually really just getting into IoT. I've done considerable amount of reading and had discussions with other developers about IoT, but I'm probably right at this moment maybe not the best source to answer that question. I would hope to in the next 6 months or so to have a better understanding of it. But from my perspective right now, um, what I think is important is that the IoT devices themselves, because they have a very low tolerance to energy usage, right? So their power sources are limited. Those IoT devices can't really deal with a pub sub, at least an incoming to them, to the device's pub sub, uh, um, architecture, because they would be constantly, in essence, pulling for a message to come into them, or some other device or server near to them would have to be doing that on their behalf. What I think is that those devices would benefit much more greatly by direct asynchronous messaging. So if we could put a very limited um, Akka actor system on a device like that, then they would only receive a message when a message needs to be sent to them. However, the device itself could use PubSub to report its state to, a system or in essence, a bounded context that's listening for that. So it could use PubSub to publish because it's only using power to send a message out, and so it doesn't necessarily need to know where this message needs to be delivered. But I think that there's potential for greater use of power with IoT devices by direct asynchronous messaging.
Yeah, and in fact, there's a couple stories on the lightbend.com website under case studies that talks about actually using Akka in IoT devices such as Eero, a kind of Wi-Fi mesh for the home that apparently everyone loves. Well, Vaughn, I really appreciate you joining us today and taking the time out of your training and consulting and writing and speaking and traveling schedule to join us. Uh, I think this has been a wonderful presentation. I hope everyone enjoyed having this excellent presenter join us today. You will receive a link to these resources next week, as I said, from somebody at Lightbend. And you can definitely go to vaughnvernon.co to find Vaughn's details and bring him to your company to explain all of this good stuff over again to your team. So again, Vaughn, thank you so much for joining us, and have a wonderful day, everyone.
Thank you.